All right, so today we're going to talk in the sort of second installment about basic structures, about the L structure. So this is a little bit more complicated than a base plate, but not by much. So basically what we're talking about with the L is a simple base plate plus some type of a vertical member. And the L is most useful, I would say, for sort of suspending some stuff. So the vertical member can serve as a kind of anchor point for something that you want to suspend out over the base plate. It could be a shaft that you want to attach something to. It could be, another vertical member, something like that. But you want to get it up off of the base plate and have it suspended. So this kind of outline that I've drawn here in dotted lines is just, some simple shaft that we're going to suspend over the base plate. So I also want to call attention to something I'm doing when I'm sketching, which is that when I try to draw lines, I try to draw them in one continuous stroke. And so you want to try to be bold in your strokes and just make them all at once, rather than, as you might be used to sketching in pencil, kind of working the pen back and forth as you move down along the line. In general, your sketches will be a lot more clear and a lot more effective if all of your strokes are kind of single strokes. And it's okay to do multiple long strokes of the same line, that's fine. But you want to avoid the case where you have this sort of feathered looking line that results from moving your pen back and forth. All right, so I just labeled my sort of suspended stuff, pretty generic, but just indicating that the L is useful for suspending things over the base plate. I'm going to finish up with my cutout lines here. And so the same principle goes with the cutout lines. Try to make them in one clean stroke if you can, rather than sort of working the pen back and forth and winding up with a kind of feathered looking line. So for the rest of the tutorial, I'm just going to walk through a couple different implementations of the L structure that have kind of different structural properties. And generally what you want to think about, you want to think about, of course, the geometry of the thing. So, what is the ratio of the length of the base plate to the length of the vertical, for example, or do they join at exactly, a 90-degree angle where the vertical is flush to the base plate at the edge, etc. And so I'm drawing kind of the simplest possible L that's made from two flat sheets that may have been, these could be plywood, these could be laser cut plastics like acrylic or Delrin, or even plastics that are cut on a bandsaw. They could be sheets of metal. It doesn't really much matter. The general properties will be the same, but the particular strength or stiffness may depend on the material that you choose. So in this case, I just have two simple sheets, and right now what I'm drawing are some fasteners that I will kind of use to indicate that I'm joining the two pieces together with screws. And so if these are metal and the vertical member has been drilled and tapped, these might be machine screws, since machine screws are designed to mate with pre-existing threads. If, for example, these were plastic members or wood members, maybe I've drilled a pilot hole, but I want to use some type of a self-tapping screw that has a sharp end to really bite into the material. So in this case, I'll just label them as sort of either bolts or screws. So if you've ever looked at the construction on the original MakerBots, in the vertical member, they would have an actual slot into which they would insert a nut, and then you could actually drill a clearance hole in the base plate and put a bolt through and thread the nut onto it and use the nut and the bolt to kind of clamp down between the base plate and the vertical portion of the L. Okay, so I just finished that guy off with some cutout lines. And I'm going to move on to kind of the next most sophisticated implementation of the L. So rather than just joining the two members flush with the edge of the vertical joined flush to the surface of the base plate, the next thing I could do is kind of use a standard wood joinery technique and create a joint that's called a Dado joint. And so the Dado joint just basically looks like a slot in the base plate that the vertical member actually fits into. So here I'm just finishing off the vertical member. So I'm actually, in this tutorial, I'm kind of drawing an exaggerated 1-point perspective. It's just sort of easy for me because the vertical and horizontal lines meet at 90 degrees, they're parallel, etc. So it makes drawing kind of the front faces of things really simple. And I only have to worry about one set of perspective lines converging to one vanishing point. Okay, so I just labeled my dado joint there. I'm going to go through and highlight my edges with my cutout lines. I could also similarly reinforce this dado joint with screws the way that I did on the L that I just drew previously. And of course it would be sort of stronger and stiffer because of the mechanical interconnection of the dado joint than the previous L shape that I drew. Now if I want the vertical member and the base plate to fit together flush at the end, but I want something that might be a little bit stiffer than the second L that I drew. So rather than just move the vertical member over to the very edge of the base plate, I could use a rabbet joint, which is similar to a dado joint. It's sort of like a dado joint at the very edge of the base plate. And so what this looks like is kind of like a notch that's been kind of cut out in the base plate along the back edge, and that enables me to join the two so that they're flush and they meet at a perfect 90-degree angle. And so I'll just label this joint. It's a rabbet joint, R-A-B-B-E-T, not to be confused with the fluffy white animals that hop around. And once again, just finishing it off with single strokes of cutout lines around the edges. Okay, that's all well and good if I have, sheets of plywood or sheets of plastic. But what happens if I want to get serious and I want to make this thing really stiff? I'm, bearing much larger loads now. I probably want to make the L out of metal. And while I could use all of the joining techniques that I've already kind of demonstrated with my first few sketches, in this case, let's explore what a welded L might look like. So welding is a process that's unique pretty much to metal. So you can weld plastics, but typically when people talk about welding, they're talking about metal, and it's a process where you're sort of simultaneously melting the two pieces that you're joining together and adding some filler material or filler rod. And so I've drawn these kind of quarter circle shaped cross sections for the welds. The size of the welds will be sort of grossly exaggerated just for demonstration purposes. Draw the edges of the welds, put a curve on that last edge that's farthest away from us, and then maybe go through and kind of add some indications that these are sort of curved. This is curved geometry here, and I'll call it out with a little arrow. Okay, these are welds. This piece is welded, and just so that I'm just going to kind of draw the symbol that you might see on an engineering drawing. And so if we look at this horizontal line that I just drew, there's a triangle on top of it and a triangle below it, and they're aligned. And so what this means is that the weld seam extends the length of the part, and it's welded on both sides. So sometimes those triangles will be offset from each other. Sometimes they'll have numbers next to each other indicating, how long the seam is. They might have a number indicating how many seams and whether the pattern repeats how many times, things like that. So this second to last L structure that I'm drawing is all manufactured in one piece, and it is extruded. So extrusion is the process where you take a ductile material and you push it through a die that has a particular cross-section that's been cut out of the die. So a hole that's cut in the die that forms the cross-section of the material when it is pushed through. And so in the case of metals, you can do something called hot extrusion, where you get the metal hot to get it very soft, and you squeeze it through this die. And it's a process that looks a bit like pasta being made, if you've ever seen that. So, you can think of pasta different types of pasta have different cross sections, like angel hair is different from fettuccine, is different from spaghetti. And so depending on the shape of the die that we use to extrude the pasta, we get a pasta with a different cross section. Same thing is true with metals. You can extrude constant cross section shapes by pushing them through die with different shapes that are cut out of them. So sometimes you see this, and it's called angle iron. So that's typically just iron that, or steel that's been extruded that meets at a 90-degree angle. Okay, the last L structure that I'm going to draw is an L structure that I've actually reinforced with another member. And so I'm kind of running out of space here, but I'm going to try to draw this as best I can. So this is an L structure where I've actually added another member, or another kind of reinforcing rib that kind of reinforces that 90-degree joint between the base plate and the vertical piece. So depending on how thick that piece is, it might be called a rib. You might also see it called a gusset, G-U-S-S-E-T. But the notion is that it reinforces the joint and makes the L structure quite a bit stronger. Okay, I'm just going to finish that up with my last kind of set of cutout lines. Oh, let me label this reinforcing rib. All right, there we go. Now I think I'll finish this up with my last set of cutout lines. And so that was a sort of lengthy exposition on a very simple structure, but the L structure is pretty common. It's going to show up in a number of machines with a number of different applications. And so seeing a lot of variants, I think, can be very helpful.